Hi, my name is Amit. I'll present a work recently accepted for publication in PRL called Limits on Spectral Resolution Measurements by Quantum Probes. I'll go over the general scenario of the NMR measurement, describe the phase-sensitive measurement scheme, and our main results. So in the general NMR scenario, you have a sample that we want to measure its spectrum, and we have a sensor. In this case, we're using an NV center in a diamond substrate, and in general, the depth of the detection volume for this NV center is set by the depth of the NV, and in each spin in this detection volume generates a magnetic field that interacts with the NV center, and also we apply a microwave control over our NV center. Overall, we can describe this interaction with an effective interaction that some kind of effective magnetic field is rotating our NV center in the z-axis, and this and the general question is, what is the spectral content of this magnetic field? And from this information, we can deduce something about about our sample, either which species that we are measuring, or the molecular structure of the sample, and okay, so each measurement we are performing is a part of a set of phase-sensitive measurements. A single measurement is done by initializing the NV center to the upstate, rotating it to the x basis, and letting it evolve under the effect of the magnetic field and our control, eventually rotating it back to the z basis and measuring the population of the NV center. And when we do that, we also record the exact time with an external local oscillator, and if we repeat this several times, we have a time series of our signal. And if our signal have some kind of detuning away from our control pulses, then each measurement will have different accumulated phase on the NV center. So the blue shaded area is the phase accumulated by the sensor, and each measurement will have a different accumulated phase. Here the black shaded area cancel out completely, so we have less accumulated phase, and this phase is translated into the population of the NV, and by measuring, we translate this population into the number of photons we get from our sensor. The number of photon oscillates with our with the detuning of our signal from the control pulses, and meaning that it encodes our signal and information about our signal, and we can look at the power spectrum of this signal and estimate the frequency of the signal. The problem emerges when we are trying to estimate two frequencies. If we have two frequencies, the blue and the red, in our measurement we'll only see if we look at the power spectrum, we only see the green line, the sum of both of them, and we'll have a hard time trying to figure out whether it's a signal that's composed of two close frequencies or just one signal frequency. And this is analogous to the Rayleigh criterion from optics. And in our work, we focus on this last step, the post-processing of the data. And what we claim is that with this type of phase-sensitive measurement and adequate post-processing of the data, in this case we're using maximum likelihood estimation instead of estimating the frequencies out of the power spectrum, then the resolution limit is not set by the Rayleigh criterion, but rather it scales like a single frequency estimation, meaning the more measurement we do, the better we can resolve two frequencies. So a few words on maximum likelihood estimation. Then, given our measurement data that we measured from this probability that encodes the information about our signal, the amplitude, the frequency, and the phase, then we can ask ourselves what is the best thing that we can hope to achieve given this as an estimate for the frequency. And this question is answered by Kramer and Rao. The Kramer-Rao bound states that from this probability function we can calculate the Fisher information matrix, and from that calculating the Kramer-Rao bound, and this value is the best thing that we can hope to achieve for an unbiased estimator of the frequency. So what it also gives us is that maximum likelihood estimation saturates this Kramer-Rao bound. So if we use that, then we'll eventually achieve this limit. So now the question is, how does this quantity scales when two frequencies go close to each other? So for this type of measurement, as we stated before, we have each signal frequency, measurement, and we repeat multiples of these measurement for n times, and at some time the signal is no longer coherent, either due to the coherence time of the signal or the coherence time of our local oscillator, and then we repeat the same measurement again, but now it has different, if it decohered, then it have a different phase. So if we calculate this Kramer-Rao bound for just a single set of measurements, then we can see that the Kramer-Rao bound for the frequency difference and the frequency sum diverges as the frequency difference goes to 0. And if we take more and more measurement set, then we can see that this divergence goes away, and we can, meaning that we can separate these frequencies beyond the Rayleigh limit. The number of sets here correspond to this number, so two sets will be this, and more sets as we continue measuring. So what is the intuition for that? Let's look at the single frequency estimation, but now the frequency goes really close to 0. This is analogous to the case where we're trying to estimate two frequencies, and we know the central frequency, the mean frequency, but we're trying to estimate the difference. So with this measurement scheme in mind, we can write down the probability function for each measurement, each single measurement, where this phi is the phase accumulated by our sensor, omega is the amplitude of the signal, tau is the measurement time for a single measurement, and delta is the frequency, and phi here is the phase of the signal. So for small amplitude and small delta close to 0, we can simplify this expression by this, and from here we can see that if we do a sequence of measurement up to the coherence time of our clock, then the only thing we can estimate are this term and this term, meaning we can only estimate these. But unfortunately we have 3 independent variables, so we can't really, from estimating these 2 quantities, we can't estimate the frequency. But what happens if we add another measurement set, a second measurement set? In this case it will have a different phase, meaning we'll get 2 more constraints that we can estimate with different phase, but we'll only get 1 more free variable. And if we continue in this with this idea, then each time we'll add 2 more constraints, but only a single free variable. And that way we can estimate delta and avoid this divergence we saw for a single measurement set. And indeed, if we generated with the help of the group of Fedora measurements on an epicenter from a signal that is from a microwave signal. In this case, there were 2 frequencies very close together, and in the power spectrum we can't resolve these 2 frequencies. We only see a single peak. This blue line corresponds to this power spectrum, but from the maximum likelihood estimation we can clearly see 2 distinct peaks, meaning we have 2 distinct frequencies. In the case that there really is a single frequency in the data, we can see that the power spectrum in these 2 cases are similar, but the maximum likelihood estimation really shows us that we can't really say that there are 2 frequencies in this data. And here we can see the same result, only in the difference as a function of the difference in the frequency. So if there is a single frequency, we can see that we can't really say that there are 2 frequencies because the peak is really close to 0. But if there is 2 frequency, then we can see a distinct peak away from 0, and we can argue that there are 2 frequencies in the data. But what happens in the case of a signal that is more similar to an NMR measurement? Then in an NMR, unpolarized NMR measurement, each time we lose coherence, also the amplitude changes. So if we have this probability function, each time we'll get 2 more constraints. Each dataset will give us 2 more constraints, but also 2 extra free variables to estimate, and this poses a problem. So our solution for that is realizing that the amplitude doesn't contain much information about the frequency, so we can just average over these different amplitudes, meaning working with a probability function that is the average probability function over the amplitude. This way, each new measurement set only adds 1 more free variable and 2 more constraints, and we're back to the same scenario we were before. We tested this idea in simulation. We simulated a signal that each time had a different amplitude and different phases, each dataset, and we see here in blue the Cramer-Rao bound for this average probability function, and here in orange the Karama bound for the probability function that is not average. You can see that this goes and diverges. The frequency comes close to 0, but see that our estimators does not diverge and stay roughly constant up to this area, and this black dashed line indicates the 2 and 3 sigma separation, meaning that all the data points that are in here, we can estimate that there are 2 frequencies with more than 2 sigma separation, but which is in good coherence with our statement that we can avoid this divergence. And thank you.